So, hello to everyone who's watching on YouTube. Uh, we'll just start in. Let's start in like 10 minutes. I'm just waiting for a few people to join the session in person. If no one joins, then we'll get started anyways in 10 minutes. Till then, I'll just mute myself. Okay, so since no one has joined the session in person yet, I guess we can just get started nonetheless. So, hello to everyone who's watching on YouTube. Just to reintroduce myself, I'm Lakshya Saggi, the problem solving TA for the Tuesday 6 to 8 p.m. sessions for the NPTEL Selected Topics in Algorithms course. And this is, I believe, the week 5. So, we'll be discussing, this will be a fifth session. So, we'll be discussing the week 5's content. So, which will include like introduction to Markov chains and yeah, so whatever was covered in this week. So, quite a few notions of probability and what are Markov chains, some introductory problems related to Markov chains, and so on. So, yeah, so uh, I guess we can just get started then. I'll just I'll just share my screen then. Let me just share my screen, guys. Yeah, I hope my screen is visible to everyone. So, yeah, I guess this won't be too long of a session. Because I usually prepare these questions and everything, keeping in mind that like someone will be present in the meeting and may ask some doubts, but since there is no one present physically present in the meeting, so uh, I guess we'll just start with summarizing whatever was covered in this week's sessions in the lectures. So note that while going over the summary, I'll of course assume that you guys have gone through the lecture videos before watching this session, because these 2 hour sessions are in no way substitute to the extensive lecture videos. So yeah, so this is more of a like revision kind of a session, and then we'll discuss some problems related to whatever was covered in this week. So yeah. So maybe we can get started then. So what are Markov chains? So mathematically, Markov chain is a stochastic process, x where uh, this x1, x2, etc. is essentially a random variable x indexed by, uh, let's say, times. So essentially, Markov chain is stochastic process, meaning that the random stochastic process is essentially a process where a random variable, the value of a random variable, the values of random variables keep changing over time. So it's x1 is the value of the random variable x at time step 1, x2 is the variable's value at time step 2, and so on. And so this is what is a stochastic process. And what's Markov chain? So Markov chain is a special kind of stochastic process where this property holds, where the property is that uh, the probability that the random variable capital Xi takes the value small xi is independent, given that the random variable has taken this random variable capital X has taken some values in the past I minus 1 time steps. So that actually this value is independent of the time steps I minus 2 and before. So whatever the random variable takes the value, like, so whatever value the random variable takes at time step I is kind of on a like, uh, this is not exactly what I'm, this is not exactly what, say, but you can think of this intuitively that at the random variable x at time step I takes the value small, and whatever it takes the value, it is independent of whatever it took the values at time steps I minus 2 or before. So essentially, like the probability that capital Xi is small xi, given the capital X's values at previous time steps, is actually just equal to the probability of xi given at time step I minus when it took the value xi minus 1. So essentially, uh, uh, you just need to know, so to find out the probability that a random variable x will take some value small xi at time step I, to find this probability, you just need to know this probability, like with what probability did the random variable take the value xi minus 1 at time step I minus 1. You don't need to know the whole past of the random variable. You just need to know what the values did it take at just the previous time step. So to know the value of the to know the probability distribution of a random variable x at time step I, you just need to know its probability distribution at time step I minus 1. And if a random variable follows this kind of a property, like it's independent of the further pass, like what values did it take at time step I minus 2 and before. So if this property holds for any random for any stochastic process, then this is called Markovian property, and essentially then that stochastic process is called a Markov chain. And this is like a really neat and yeah, very useful concept in, like, I believe, a lot of mathematics, a lot of computer science and whatnot. So yeah, this is one of the central, like, concepts and very useful in all mathematical domains. So yeah, so essentially, uh, what's a really good thing about this Markov chains is that uh, mm, the Markov chains can be like, so to essentially know what happens at time step I, you just need to know what happened at time step I minus 1. So Markov chains can be described very succinctly. You don't need to describe the distributions of random variables for all the time steps I minus 1, I minus 2, and so on. You just need to know distributions at time step I minus 1 to know the distribution at time step I. And essentially, like with what probability the random variable takes the different values, it's described using the state transition probabilities Pij. So essentially, it says that suppose at time step I minus 1, random variable took a value, let's say some uh, k, then Pkj will represent the probability that now the random variable in the time step I will take the value j. So yeah, so Pij is the probability that the next state is j given the current state is I. So this can be thought of as a transition probability. That suppose at time step I minus, or maybe at time step t minus 1, you are at value I. Then with what probability at time step t will you go to the value j? And this is what essentially describes the whole Markov chain at time step t. So that's why, like, Markov chains can describe very simply, and there are beautiful results related to Markov chains. So yeah. And then, of course, there are some basic notions and definitions associated with Markov chains. So, uh, so one of the things is called hitting time. So suppose we are given a starting state where our process starts. Then what's the expected number of steps needed to reach another state in the Markov chain? So so suppose you start at, let's say, suppose this is kind of the Markov chain that from state zero, you can move to state one probability one, from one you move to state two probability half, and yeah, so on. So these are the transition probabilities. Then let's say what's the expected number of steps required to reach from, let's say, state zero to state n. So one can essentially, like, there's a path where you can reach from zero to n uh, in a straight line. But note that the probability with which this path will occur is just product of all these terms. So one times half times half, and whatever. And then there will be some other paths also. So with probability one, there is a transition from zero to one. But now it can go back from one to zero with probability half, or it can go from one to two with probability half. So there will be like so there will be another path which occurs with, like, let's say, lesser probability, which will be like this. So it goes from 0 to 1, then goes from 1 to 0 back, and then goes from 0 to n, and so on. So this path is longer and it has some different probability. So now with respect to all the possible paths and with respect to their probabilities, one can calculate the expected number of steps taken. Like so this part takes n steps, but this part takes n plus 2 steps, and so on. So one can find the expectation of, like, going from state 0 to state n in a Markov chain. And this is called, like, hitting time. And so hitting time is essentially, like, not for the whole Markov chain, but for a pair of states. Like suppose you're starting at state, let's say, I, and you want to end at state j, then what's the hitting time for starting at I and ending at j? So yeah. So the hitting time is an important notion, and similarly, there are other important notions in a Markov chain also. So, for example, there is the notion of mixing time. So, what's a mixing time? So, suppose given a start state, does there exist any limiting distribution? So, yeah. So, what do we mean by limiting, what do we mean by limiting distribution? Sorry. Yeah. So what do we mean by limiting distribution? So essentially, limiting distribution is a distribution. Okay, maybe limiting distribution its definition will come later on, or oh, okay. I think I forgot to include the yeah. Maybe I forgot to include the definition of limiting distribution, or maybe it wasn't covered in the lectures properly. But yeah. So what's a limiting distribution essentially? So in a Markov chain, we know like how the random variables distributions will evolve, like how will X evolve. We know from transition probabilities and all that they will be like, suppose we are given some starting state that at time step one, the random variable distribution looks something which is given to us. So that's called the initial distribution, let's say X1. And now we know through the Markov chain how will X2 look like, how will X3 look like, how will X4 look like, how will Xi look like, and so on. So limiting distribution is essentially like what does the distribution of x looks like at time step infinity. So note that it need not even exist, because why should a limit for this kind of a thing always exist, right? Like why does this always have to converge at a limit with this x1 x2 until xi? And then the question is, if it exists, then is it even unique, and irrespective of whatever start state we choose. And this is true, then Uh, if the limiting distribution exists, then another important thing is to know how many steps does the Markov chain, how many steps do we need to go into the Markov chain to go epsilon close to the limiting distribution. So how much time do we need to spend? So at what time step t, like maybe x1, x2 till x3, like at what time step t, the distribution xt looks close to x infinity or something like that. And this time is called mixing time. But note that this notion of mixing time will only exist if there exists a limiting distribution, and if it is unique. Because if it is not unique, if there are multiple limiting distributions, then with respect to which distribution will you be taking the closeness? So yeah. So yeah. So first of all, yeah. Before even that, before even the uniqueness, the existence is also not always guaranteed. The existence of a limiting distribution is not guaranteed in a Markov chain. So this example was covered in the lecture. So for example, consider this Markov chain where there are two states, 0 and 1, and one you transition from 0 to 1 with probability 1, and if you are at 1, you transition to state 0 with probability 1. So here there does not exist any limiting distribution, because suppose the limiting distribution because suppose and this is because, like, if the initial distribution, suppose you to x1 was just you started at this state 0. So if you started at this state 0 with probability 1, if x1 is the distribution where you are at state 0 with probability 1, then at time step 1 you will be at then x1 will be the distribution when you will be at state 1 with probability 1. Then at x2, you will be at state 0 with probability 1. At x3, you will be at state 1 with probability 1. So you'll keep alternating between 0 and 1 at alternate time steps with probability 1. So as you can see in the, like, taking the limit, like, actually it won't converge like to a single value. Because at any point of time, either you will be at if the time is even, then you will be at 0 with probability 1. And if the time step is odd, then you will be at 1 with probability 1. And that's why no limiting distribution exists for this kind of an example. Yeah. Yeah. But if we have started, like, but note that this is only true like if, like, what I just described, like no limiting distribution existed. If in the initial state we took that like we started at this state 0 with probability 1. That's why we kept alternating. But suppose instead the initial distribution was such that the x1 distribution is such that you are at state 0 with probability half, and you are at state 1 with probability half. Then at x2 also you will be at state 0 with probability half, and you will be at state 1 with probability half. And so x1, x2, x3 and all will actually be the same, which will be the distribution will be that you are at state 0 with probability half and you are at state 1 with probability half. So yeah, so uh, taking now if we take initial state as something different, then actually we see that the limiting distribution actually exists for this Markov chain. So this notion of limiting distribution is kind of related to like so the existence of limiting distribution is closely related to the initial state which you choose. So or the initial distribution which you choose. If the initial distribution was like something like this, where x1 is 1 or something, then it did not exist. But if the initial distribution looks something like this, then actually limiting distribution exists. So these are uh, quite important concepts to keep in mind. Similarly, so yeah, so there will be a lot of definitions because we are introducing a lot of new concepts. Similarly, now what's periodicity of a Markov chain? So a Markov chain, so essentially like a periodicity, like on a very high level before going to the definitions also, one can think like what is periodicity? So as we have always understood periodicity, so periodicity is essentially something takes a value. So a function is periodic if it takes uh, some value at regular intervals. And so essentially like there's a similar thing for periodicity of a Markov chain. So Markov chain is called periodic if there exists a positive integer delta, uh, such that probability that x probability of x at time step I plus L is A, given xi is A is 0, unless L is divisible by delta. So essentially what it says is that uh, uh, for uh, uh, for a state A, let's say so for a state A, the periodicity of that state is essentially the smallest number delta, such that uh, between time steps, let's say t and t plus delta, it always takes the value 0. Like you cannot reach the state A in t time steps. In delta, like um, if you are at state A at some point of time, then you cannot reach the state A again before delta further steps, time steps. So essentially, like the time steps, the time intervals at which you can reach the state A are essentially multiples of delta. So that's kind of what is called the periodicity of the Markov chain. So yeah, like essentially you can think of it as the like if you think of this probability distribution as the function, then essentially this function takes non-zero values only at multiples of delta. This probability function. Yeah. So that is what is called periodicity of a state. And yeah, uh, and yeah, and Markov. So essentially, if you are calling this periodicity of a state, then what is when is a Markov chain called periodic? So Markov chain is called periodic if any of its state is periodic. Only then do we call uh, Markov chain as periodic also. So I'll just mute myself for a minute, guys. I'll be coming back in a minute. Yeah, I'm back, guys. Sorry for that. So yeah, essentially we are saying that yeah, so essentially periodicity uh, is the timing interval like let's say delta such that like at every time such time step now bit at every such time step delta like like if you take like the time interval t plus delta t plus 2 delta and so on, then probability at any point of time between these intervals is actually zero. Like this function is zero. It can be zero at these values. Yeah. So it is like zero, and one can actually uh, like have an equivalent definition for periodicity of a state. So if you consider all the time steps such that probability xl equal to a given x1 equal to a is not equal to 0, if you consider all such time steps, then state A is called periodic if and only if GCD of all such time steps is actually not equal to 1. So if the GCD is not equal to 1, then actually like they are occurring at some distance delta. Like if GCD is delta, then they are occurring at like after every delta units of time. So yeah, and yeah, and if a Markov chain is not periodic, then it is called like aperiodic, of course. So how can one? So yeah. So okay, I think we also have not discussed what's a stationary distribution. So yeah, okay. So what's a stationary distribution? So stationary distribution P for a Markov chain. So let's say or pi. So let's say P is the transition matrix for the Markov chain. And what's a stationary distribution? Stationary distribution is essentially a distribution at which if you start your Markov chain, then your Markov chain remains the same throughout. So if you start at a distribution pi, then if pi times p is equal to pi, then the distribution pi is called the stationary distribution. So for example, here in this example we discussed, so this distribution x1, where like state 0 is its probability half, state 1 is probability half. After transitioning using the transition matrix P for the Markov chain, you essentially arrive at the same distribution again. So if this is pi, then pi times P is also equal to pi. So this is actually a stationary distribution for this Markov chain. So yeah, and yeah, so these stationary distributions are actually important objects. And uh, how can one like and of course like so note that uh, mm, yeah. If note that period of a Markov chain can always be equal to 1, because one can always say because between xi and xi plus 1 there is nothing in between. So this thing trivially holds. But if like period is 1, then we actually say the Markov chain is aperiodic. Only when period is greater than equal to 2 is when it makes sense. And if period is 1, if and only if it is aperiodic, and period is greater than equal to 2 if and only if it is periodic. So, uh, so I think there was a mistake in the lecture. So what we want to do is, suppose we want to ensure a periodicity for a Markov chain without changing the stationary distribution. It's not enforcing periodicity, but let's suppose we want to enforce a periodicity. Then how can we do that? So suppose we are given a possibly periodic Markov chain, and now what we want to do is we don't want to change its stationary distribution, but we want to make it aperiodic. Then what can we do? So suppose P was the transition matrix for the Markov chain. Let us define new set of transitions. Uh, let's say we define a new kind of a Markov chain, which is like Q, which is equal to P plus I divided by 2. So we have defined a new Markov chain, and we'll say that so essentially like this Markov chain, you can see that it is aperiodic, because now what's going to happen is that every time step for any state I, you have a transition from that state to that state itself with probability half. So uh, yeah, so if you are at state I, then you will be at state I at time step t plus 1 also if you are at state I at time t with probability half at least. So essentially period cannot be greater than equal to 2. So that's why this Markov chain has become aperiodic. And actually, one can also prove that pi of q. So one can also prove that this also has a stationary distribution, and the stationary distribution for this is actually equal to the stationary distribution for p. And why is this true? So this was also discussed or proved in the lectures that we are given that pi, suppose pi is a stationary distribution for the Markov chain P. Then for the Markov chain Q, let's say what does pi of Q look like? So pi of Q is nothing but pi times P plus I divided by 2, which is pi P by 2 plus pi I by 2. And we know that pi times P is just pi because pi was stationary distribution for P. So this can be replaced by pi, and pi times I is also pi. So this is pi by 2 plus pi by 2, which is pi. So we have shown that pi times Q is actually equal to pi. And Q was like Markov, like the different Markov chain. So pi is also stationary distribution for the Markov chain Q. And now, so essentially, from the starting possibly periodic Markov chain P, we have obtained a new Markov chain Q, which is aperiodic, but it always has a but it has the same stationary distribution. So yeah. And why are these concepts of like periodicity and stationary distributions important? So this is because there is a fundamental theorem of Markov chain, which says that any finite, irreducible, and aperiodic Markov chain has a unique stationary distribution. And moreover, the Markov chain converges to its stationary distribution irrespective of its start state. So essentially, yeah, Markov chain converges to its stationary distribution means kind of like the limiting distribution for the Markov chain is actually the stationary distribution irrespective of the start state. If the Markov chain follows this property, finiteness, irreducibility, and aperiodicity. And what are these properties? So a Markov chain is called finite if its state space is finite, as you can guess. What do we mean by irreducibility? So a Markov chain is called irreducible if for every two-state phi in J, probability of reaching I from J and probability of reaching J from I both are non-zero. So they need not be equal, but there should always exist non-zero probability of going from I to J and non-zero probability of going from J to I. And the third condition is that the Markov chain should be aperiodic. If these three things are true, so we won't be, so the proof of this theorem was not discussed in the lectures, I believe, but if these three things are true, uh, then the Markov chain has a unique stationary distribution. And yeah, the limiting distribution actually is equal to the stationary distribution, irrespective of the start state. So let's just see the example which we covered initially. Like we said that for this example, actually limiting distribution was not equal to stationary distribution for some start state. So this must have failed some condition of the like fundamental theorem of Markov chains. So as one can see, like the three conditions were the Markov chain should be finite. So there are just two states, so it is a finite state space. But also there was a condition that it should be irreducible. And you can see that there is just one pair of states which is 0 and 1. So 0 is reachable from 1 and 1 is also reachable from 0 with non-zero probability. So this chain is also irreducible. But one thing where this chain lacks is like this chain is actually not aperiodic. Right? Why is this the case? So essentially you can see that if you are at state 0, then you can then only after two time steps can you come back to this state again. So essentially, like if you are at state 0, then at time step t plus 1, you'll always have a non-zero probability of being at state 0, or a zero probability of being at state 0. So and then so yeah, so essentially so essentially what this means is that this Markov chain is actually periodic with a period of 2, because only after 2 time steps can you come back to the state 0. So yeah, so that's why this Markov chain is actually periodic with a period of 2, and that's why the conditions of fundamental theorem Markov chain failed in that example, and that's why it did not have a like limiting distribution equal to the stationary distribution. Okay, so if that makes sense, yeah, then yeah, so this is like a very like one thing is like this is a very important property for Markov chains. That's why uh and yeah, so the example in which we discussed, the example where there did not exist any limiting distribution. Actually, one can like if you add those the kind of self loop transitions probability half like we did here, then we'll obtain another Markov chain. And actually, for that Markov chain, you'll have a stationary distribution, and that's like a neat thing to have. So essentially, we can convert any Markov chain to so we can convert any finite and irreducible Markov chain to a finite, irreducible, and aperiodic Markov chain without changing the stationary distribution. So yeah, so this is pretty cool to have. And this fact is like turns out to be pretty useful in a lot of applications of Markov chain also. Okay then. So then there's another thing which is called there's another notion like of like suppose you are given two distributions. So previously we mentioned like being epsilon close to the stationary distribution is like called the mixing time. So how do we even measure this epsilon closeness? So essentially, how do you measure distance between two distributions? Like given two probability distribution, how do you say that how far are these probability distributions? So there are various notions of distances present in the literature like K divergence and so on. But one of the notions which was covered in the lectures was total variation distance. So given two distributions P and Q, the total variation distance between P and Q is just supremum over P of A minus Q, the mod of P of A minus Q of A over all the possible events. So essentially, what this essentially says is that so if you are given distributions P and Q, then what's the set of events, let's say, yeah, yeah. What's the event for which this value, the probability of A minus like probability of P of A is like the probability the event A occurring with respect to distribution P, and Q of A is the probability of A occurring with respect to distribution Q. So for what value or like for what event is this value maximized, P of A minus Q of A? So maybe this was not discussed in the lectures properly, but actually, yeah. So the proof is not too difficult, but I won't cover it right now. So total variation distance between P and Q. So this is one definition, and one can also prove that this is equivalent to saying that, yeah. So this is actually equivalent to saying something like this. Mm, yeah, let me just, yeah. Uh, so here, yeah, yeah. So maybe I'll just write it. So total variation distance actually can be written something like this also. So so essentially like like uh hmm, yeah. So how can we think of this? So should we read? Yeah, okay, I guess it's fine. So total variation distance is essentially saying, so you have like so this P and Q, so these are like probability distributions, like assigned to some events, right? And then you can take a set of events together, you can take their union, you can take their intersection, whatever, and then those will also have some kind of probability distributions. And now the set of events which you take together, the total variation distance is nothing but the maximum value of this P of A minus Q of A. And actually, one can actually prove that this is actually equal to just half times summation over all the possible values which this x can take, or essentially like set of all possible events. So total variation distance is nothing but uh, half times summation over x, the value p of x minus q of x, and like it should also have mod. So if you take this value p of x minus q of x, the unsigned value p of x minus q of x, and yeah, you sum it over all possible x uh, and take its half, then actually that is equal to the total variation distance. So yeah, so this is like, so think of like, so to get a bit of a clarity on this, just think of maybe like mm, this x to be maybe, let's say, a random variable. And then this P and Q are maybe the distributions over of this random variable. So essentially what we are saying is that hmm, uh, like uh, so this set A is nothing but the set of values at which this random variable like the set A is just the set of values which this random variable takes, at which this P of A minus Q of A values is maximized. And this can be thought of also as like you just take sum over all possible or like you can also say it's an integration if these are continuous distributions. But if these are discrete distributions, then you can just take summation. So you just take sum over all possible values of this random variable x, and you take consider the value p of x, and you consider the value q of x, take its difference and sum it over all possible x. Yeah. And this formula is like quite useful for total variation distance. And this kind of will be useful in one of the questions also. So yeah, so this is like something which you should keep in mind. Maybe it was not discussed in the lectures properly, but yeah, this is important. And then what's mixing time and coupling? So the mixing time we already described. So mixing time of the Markov chain is just, we described it informally that the Markov chain should be epsilon close to the stationary distribution pi. Uh, and then, yeah, so how do we measure this epsilon closeness? So this epsilon closeness is usually measured in terms of like total variation distance. So for an epsilon greater than 0, mixing time T mix of epsilon of the Markov chain is the minimum possible I, such that total variation distance between xi and pi is less than equal to epsilon. Yeah, and this should hold for like yeah, yeah, the minimum possible I. And like I think yeah, so this is the definition for mixing time. And then what is coupling? So a coupling of two random variables, so x and y. Yeah, I'm having a bit of struggle with scrolling, but yeah, I guess it's better. A coupling of two random variables x and y with distributions mu x and mu y is a joint distribution. So coupling of random variables is nothing but, suppose you are given two uh, random variables x and y with distributions mu x and mu y, and now you couple them, or essentially you make a joint distribution out of them. So mu x y or x comma y. such that the marginal distributions of mu xy are x and y respectively. So what are marginal distributions? So I hope you know what are marginal distributions of the probability courses. So, so essentially what does marginal distributions actually mean? So if you consider the distribution mu of x comma y, so if you fix some value of x and then you sum over all possible values of y, then that sum should be actually equal to mu of x itself. So what it's saying is even though these distributions are coupled, uh, these x and y, but they also retain their original distribution mu x and mu y in some sense. That is called coupling. And yeah, so one can actually show using this definition of coupling, a coupling lemma, which says that for any two discrete random variables x and y, so this is a quite useful lemma. For any two discrete random variables x and y, we have that always the total variation distance between x and y is less than equal to the probability that x is not equal to y. And one can actually show that this upper bound holds also in some cases, as we'll see in one of the questions. So, between any two distributions x and y, the total variation distance is always less than equal to the probability that x is not equal to y. Although directly y, one might think that why is it called coupling lemma, but its proof was discussed in the lecture that it was through coupling. So yeah, that's why. So coupling the random variables x and y and then obtaining. But yeah. Then there is this concept of reversible Markov chains. So we know that what's the stationary distribution? So a stationary distribution of a Markov chain is distribution pi, such that pi of p is equal to pi. And note that this equation gives us like n linear equations in variables pi 1 till pi n, so that pi 1 sum of pi 1 till pi n is actually equal to 1. And yeah, for any pair of states, what this essentially hmm, yeah, and what's the detailed balance equation? So suppose instead of looking at this equation itself, we say that okay, for any pair of states, suppose we are starting at state pi I, and then we move from this state to the state j. We are just starting from let's say, yeah, we are starting from the state I with priority pi I, and then we move to the state j with priority pij. Then if pi I times pij is equal to pi j times pi p of ji, then such a Markov chain which satisfies these detailed balance equations are called reversible Markov chains. So note that one can find the stationary distribution using just this equation, pi of p is equal to pi. And from this you will obtain these values pi 1 till pi n. And after obtaining these values, one can see whether these pi I satisfy these kinds of properties. That if I have a state I, uh, there with probability pi I, then if I move to state j from here, is it equivalent to, is the probability of this equal to starting at state j and then moving to the state I? So if this happens, so kind of we are going from I to j with equal probability in the stationary sense, and from j to I with equal probability in the stationary sense. If these kinds of things are happening, then we call this reversible Markov chain, because we are going from I to j with same probability mass as the mass with which we are going from j to y. And this should hold for all pairs of I and j. So note that this is a very nice property to have, but this is always not possible. Yeah. So note that uh, like there can of course they can exist Markov chains which have a stationary distribution, but they are not reversible. Yeah, and it's not too hard to see why. Yeah, and actually one can go the other way around. Actually, if we are given a reversible Markov chain, then if any distribution pi satisfies the detailed balance equation, then it will indeed be a stationary distribution. And why is the case? Because yeah, we know this what's the formula for stationary distribution. So essentially, if the probability mass going out of a state for any pair of states, like going out from I to j, is equal to the mass coming from j to I, then actually the probability mass at the state I does not change. And that's why it's a stationary distribution kind of a thing. So yeah. So any distribution satisfying detailed balance equation is in itself a stationary distribution. And this is like somewhat useful as we have discussed in these random in the applications of Markov chains in the lectures, as has been discussed in the lectures. So yeah. And then in the lectures, there were discussions around some applications of these Markov chains. So for example, like uh, random walks on undirected connected graphs. So what's a random walk on, let's say, an undirected connected graph? So suppose we are given a graph G with the vertex at V and the set E, then uh, Pij, so uh, suppose we associate the probability like of moving from a state I to a state J as the probability Pij, or state here is just the vertex. So moving from a vertex I to vertex J is noted by the probability Pij, and it's just equal to 1 divided by d of I, where d of I is just the degree of the vertex I. And if and only if like I comma j is an edge of the graph. Essentially, what we are saying is uh, we are visualizing. So what do we mean by this random walk on these undirected graphs? So we are kind of trying to visualize these undirected graphs as Markov chains, where these transition probabilities, the values of these transition probabilities are given like this. Essentially, you can see that since there are di edges going out of the vertex I, because like degree of I is, so this is the definition of degree of I. So then like if for each edge we can take that edge with probability 1 over di, then from the vertex I we are actually going out to with probability 1 or something like that. So yeah. And actually it can be seen that for these random, so essentially like now we are moving in the graph kind of randomly. If you are starting at some vertex I, then you can move to some vertex j, j prime, j double prime or something with some probabilities, and then you can move further with some other probabilities and so on. That's why this is called a random walk. And these have proved to be very, very useful. These notions of random walk have proved to be very useful in a lot of areas of computer science actually. And one can actually easily verify that the distribution given by this, that pi of I is just degree of I divided by 2 times the number of edges. So actually this satisfies the detailed balance equation. And hence this distribution is also the stationary distribution. So this really is not too hard to verify. So yeah. And this was discussed in the lecture as well. So yeah. And so since this satisfies the detailed balance equation, which is the time reversible Markov chain, it has a unique stationary distribution. And if it is aperiodic, its convergence is also guaranteed in the sense that it will also be a limiting distribution if the chain is aperiodic. And pi of I is nothing but, so this is the distribution, which will be the limiting as well as stationary distribution if it is aperiodic. Pi of I is d of I divided by twice the number of edges. So yeah. So then there was discussion around some examples of random walks on graphs. So suppose the graph at hand is just a cycle graph, then one can say that we are considering random walk on a cycle. So yeah, so we have this kind of thing that suppose, so a cycle can be visualized as also like the integers mod n. So you have the number 0 to n minus 1. And then like if you are taking integers mod n, actually n corresponds to 0, n plus 1 corresponds to 1 and so on. And then I and j have and then the numbers I and j have an edge between them if and only if the difference between I and j is either plus or 1 or minus 1 mod n. So then this kind of forms a cycle, like these transitions form a cycle. So you have the 0, 1, 2 till n minus 1. These are the numbers. And then the edges will be from 0 to n minus 1, 0 to 1. Similarly from 1 to 0 and 1 to 2 and so on. So that's why it's a cycle kind of a graph. And now, if and now, so note that a cycle is actually periodic, because now if you are at state 0, then so suppose suppose that it's how what the distribution look like. So from 0 we can move on. So suppose this is our distribution. So suppose we just say any like that the distribution which we uh, defined in this uh, random walks on graphs, where we define the transition probabilities as 1 over di. Suppose this is the Markov chain at hand. Then if this was the Markov chain at hand, then from 0 we'll be transitioning to 1 with probability half, and similarly we'll be transitioning to n minus 1 with probability half. And yeah, we won't be staying at 0 with any probability. And then from 1 we can come back to 0 with probability half, and so on. But now what's going to happen is actually you can see that yeah, so this kind of Markov chain uh, will be actually periodic, because uh, like if if you like um, if you start at state 0, then you can only come back to state 0 after 2 time steps. So you cannot stay at the state 0. Then after only 2 time steps, you can come back again to the state 0, and so on. And because of this, the Markov chain will be aperiodic if we just defined it with respect to as we defined in the random box. So to make it aperiodic, we can introduce laziness, as we already discussed in the previous section. So we introduce laziness to make the Markov chain aperiodic, which essentially means that we add self transitions with probability half, and then the outgoing transitions are with probability 1 over 4. Yeah. And actually for this kind of and now if we do a random walk on this kind of a thing, let's see how does the Markov chain or the distribution evolves over time. So it was discussed in the lectures actually that uh, the mixing you can see the proof in the lectures. I won't be getting into the proof and everything, but the mixing time for such a Markov chain is actually dependent is actually less than equal to n square times some function of log of 1 over epsilon. So essentially, total variation distance is at most epsilon after 2 log 1 over epsilon n square steps. So essentially, mixing time. So the main idea is that the mixing time for these cyclic Markov chain, what we discussed, is approximately is quadratic in number of vertices or quadratic in number of states. So yeah, this is kind of a cool thing to see, and it has quite a lot of applications. And yeah, so for proof of this, you can refer to the lectures. And similarly, there are some other applications for Markov chains, suppose you are shuffling cards. Suppose you have a set of n cards. The state space of is the set of all cards of n factorial permutations. At every step, you pick one card uniformly random from the rest of the cards and put it at top. Then, yeah. So this Markov chain is actually reversible, one can prove, and it's also aperiodic, and hence its stationary distribution is unique. So one can actually prove this was shown in the lectures that for this kind of a shuffling cards kind of a game where you're picking a card at random and putting it on top, the mixing time of the Markov chain is actually just at most n log n plus n log 1 over epsilon, where n is the number of cards which you have. So yeah, this can also be you can see the lecture videos for take a concrete proof of this. So yeah, so I guess this was all the since in this week mostly this theory was only discussed. So this is the theoretical part or the summary of the theoretical part which was discussed in this week's lectures. Uh, yeah, so we skipped a lot of the proofs because yeah, proofs can be you can see the proofs on the lecture videos, and these are more of uh, yeah, quick summary of the week's session of the week's lecture. So now maybe we can discuss I don't have a lot of questions. I just have 3 questions. But hopefully from just these three questions, you will be able to grasp most of the probability ideas. So yeah. So so first question is get started. I would have liked if some people were actually present in person in this session. Then I would have liked people to attempt this. But since no one is present, then I guess I'll just discuss the question straight away. So suppose the first question says that let P and Q be two probability distributions over some sample space of size 50. Then what is the maximum possible total variation distance between P and Q? So recall that what's total variation distance? Total variation distance was like as we discussed, like there were two alternate ways of seeing total variation distance. One can think of total variation distance as this quantity. It's just supremum over, yeah, it's just supremum over like P of A minus Q of A is mod over all possible A's. And also it's also equivalent to this quantity. But I guess this thing suffices actually. Uh, so note that total variation distance is just supremum over all these probabilities. And so this is why actually one can see that total variation distance can never be actually more than. So uh, so yeah, maybe I should add it as a note also. Uh, that so since total variation, yeah, okay, yes, no. So what I want to write is okay that mm, so given this quantity total variation distance, so this is actually always greater than equal to 0. And why is this the case? Uh, this is because this is like supremum over some mod value, and this mod is always greater than equal to 0, and so supremum over all of this. Supremum is just like uh, you can think of supremum as max. Like supremum makes sense more over like sets, like infinite sets and something. But finite sets you can think of this as just max. So yeah. So supremum will since this mod is always greater than equal to 0, supremum will also be greater than equal to 0. And note that also this P of A minus Q of A, this value will always be bounded by P of A. And P of A is nothing but probability of this set of events A happening. And hence probability of A is always bounded by 1. So this is always bounded by 1 also. So this is a quite important property that the total variation distance is always lies between 0 and 1. And also the second thing is one can show that the total variation distance is nothing but half times some overall possible values of x, the value p of x minus q of x. Yeah. So yeah. So the question is let p into v2 broad distributions over sample space of size 50. What is the maximum possible total variation distance? So yeah. So actually, so to show that something is maximum possible, we need to show an upper bound and we need to show matching instance at which the distributions take at which we need to show an instance of distribution P and Q at which the total variation distance actually takes that value. So actually we'll show that the total variation distance between P and Q can be at most 1 actually. So yeah. So we know that distance with total variation distance between P and Q is less than equal to 1. And consider the distribution P as the distribution mm, which takes uh, uh, 0. So sample space is of size 50. So let's sample space. So let's sample space for P and Q is equal to maybe S1 is state 1, S2 is state 2, and dot 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 S50, right? So, and now how do we define these P and Q? So suppose probability that for P, uh, P of S1, so essentially probability with respect to distribution capital P of having the state S1 is 1. And uh, and then like for all other states it should be 0 because probabilities over all the states is sum up to 1. So yeah, so probability of S2, probability of S3 is dot 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 till probability of S50 is 0. And what do we take Q? So essentially, what's the total variation distance? We need to essentially make P and Q as disjoint as possible, and that's when their total variation distance will be the largest. So to make Q as disjoint as possible from P, so now Q of S1, let's say we take 0, and Q of S2 dot 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 Q of S. Yeah, okay, maybe I should write as Q of S50 as 0 as 1, and uh, S1 till S49 as 0. So what we have done is like we have taken this distribution for P and we have taken this distribution for Q. So now note that the set S50 is actually the supremum, like the value. So this one value. So note that yeah, P of S50 or maybe S1 minus Q of S1 is actually equal to 1. And so supremum over all of these values like P of like some set of SI minus Q of some set of SI will be at least 1 because this set actually achieves this value 1, so supremum will be at least 1. And we know that also we know that there's an upper bound of 1. So actually this one is actually tight. And hence uh, d of dq is actually greater than equal to 1. Uh, because yeah, because for supremum we'll have that it should be greater than equal to this value. And so this is like, let's say fun, or let's say this is statement A, and let's say this is statement B. Yeah, like this is A, this is B. Yeah. So from A and B, we get that distance of PV is actually equal to 1. And so actually what we have shown is that, so we had an upper bound on this total variation distance, and we showed a matching lower bound of 1 also. And so the maximum possible total variation distance between P and Q is actually equal to 1. Matching upper and lower bound. And hence the maximum possible total variation distance between P and Q is equal to 1. So just underlining the final answer. Okay, then like straightforward question. Not too much, but just yeah, a bit of concept. that size. Okay, so now let's move on to the second question. So second question is, let the distributions of two random variables x and y be Bernoulli uh, with parameters 0.2 and 0.3 respectively. What is the total variation distance between x and y? Okay, so I hope uh, everyone remembers what are Bernoulli distribution. So Bernoulli distribution is uh, nothing but it has a single. So it's essentially you can think of Bernoulli distribution as just a coin toss. So yeah, so essentially x is a random variable, or x is a random variable which shows heads with probability 0.2, tails with probability 0.8, and y is a random variable which shows head with probability 0.3 and tails with probability 0.7. And now we need to find out what is the total variation distance between x and y. So there are two ways to look at this. One way is just finding out the supremum over all possible uh, sets of values, which takes like or other thing is calculating it using this formula. So actually we'll show it both ways so that both the definitions are uh, clear to us. So yeah, uh, yeah. So maybe I'll just write it out first. Like yeah, probability that yeah x is 0 is nothing but 0.2, and yeah, I'm just writing out the meaning of these Bernoulli variables. And probability that x is 1 is just 0.8. And similarly, for y, it's given that probability that y is 0 is actually 0.3, and probability that y is 1 is just 0.7, right? So now by the uh, yeah, by the definition of total variation distance, yeah, uh, uh, just a second, guys. Or maybe yeah. So here, like, yeah, actually, I, I realized, like, yeah, total variation distance here will be nothing but, so total variation distance will be just between x and y will be like, so there are just two possibilities, right? X is 0 or x is 1. So another possibility is the event where you take the whole set, like 0 union 1. But in that case, like, the probability that x takes the value either 0 or 1 is actually 1. And similarly, y takes the value 0 or 1 is also equal to 1. So, uh, yeah. So consider the event E1 taking the value 0 or 1. And then note that, yeah, probability of E1 with respect to the variable x. I'll just mute myself for a minute, guys. Coming back in a minute. Back right? Oh yeah. So probability with respect to like the random variable x for the event even, where variable takes the value 0 or 1 is just 1. And similarly, probability with respect to the variable y is also just 1. And so like the event even, uh, so this implies that yeah, so this won't actually serve as the purpose. So probability of x of even minus probability of y of even is actually just 0. But if we take the event of like maybe just x taking the value 0, like or the random variable taking the value 0, then yeah, yeah, consider E2. So there are just three possible events here since we are in the sigma algebra, or like four possible events that we don't consider anything in which like probabilities will be 0, or we consider that the random variable takes the value 0, takes the value 1, or takes the value 0 or 1. So for 0 or 1, we know that the this value comes out to be actually 0. And if we just consider the random variable as taking the value 0, then like what's going to happen is, yeah, this is going to be 0.2, and this is going to be 0.3. And what this means is, yeah, this is going to be 0.1. And actually, you can see that if you take the third event E3 as the event where you take the variables take the value 1, in that case also, so this thing will be reverse 0.8, this thing will be 0.7, and then also 0.8 minus 0.7 will come out to be 0.1. So actually, this is the supremum value or the maximum possible value. And that's why, mm, uh, yeah, uh, yeah. Yeah, E3 is taking the value 1, and here actually you can show that uh, this thing will just be equal to 0.1 also. And what's the like so total variation distance is the max of three values. So hence total variation distance is max of 0 comma 0.1 comma 0.1, and this is just equal to 0.1. So this is the total variation distance between x and y, 0. And you can calculate this using the formula also, which I mentioned, which is just like half of the difference of probabilities over all values of x. So if x is 0, then it's like 0.3 minus 0.2 is 0.1 plus 0.8 minus 0.7, which is also 0.1. So 0.1 plus 0.1, which is 0.2 divided by half, which is also 0.1. So from the formula also you'll get the same calculation. I just did this orally because I don't want to write the same thing again and again, but yeah. So this is the answer. Okay, now let's come to the third question. Third question is, let x and y be two discrete random variables. Suppose probability that x equal to y is 0.3, and what is the maximum possible total variation distance between x and y? So for this, we know the coupling lemma from the coupling lemma which we discussed. Uh, so coupling lemma essentially says that total variation distance between x and y is less than equal to probability that x is not equal to y. So so uh, so by coupling lemma, what do we know? We know that total variation distance between x and y is actually less than equal to probability that x is not equal to y. And I'll like write this not equal to using this. exclamation equal to mark. Yeah. So, but how do we find this probability x not equal to y? So for this, we know that yeah, that probability that the random variable x equal to y, since these are disjoint events and like yeah, complementary events also, because like either x will be equal to y or x will not be equal to y. So probability that x equal to y plus probability x is not equal to y, we know that this probability is equal to 1. So this implies that probability x not equal to y is just 1 minus 0.3, which is 0.7. So we know that total variation distance between x and y is less than equal to uh, so this total variation distance is less than equal to 0.7. So this is what we know. But like I just described previously, like okay, we are asked what is the maximum possible value. So while this will be value which will be achieved by complete lemma, but usually for finding out the maximum possible value, you just don't need to show an upper bound, because upper bound is also 1. You also need to show a matching instance at which this value is actually achieved. So can we show an instance, like can we show random variables x and y such that probability that x equal to y is 0.3, and yeah, the total variation distance between x and y is actually 0.7. So this maximum can be indeed be achieved. So I'll show an example of a distribution at which this maximum is achieved. Be achieved for the following distribution. So what's a distribution? So suppose for random variable x, we say that these are discrete random variables. Suppose probability that x equal to y, x equal to 0, I say that this probability is yeah. Okay. So yeah. So suppose x and y are independent random variables. So suppose we are assuming that they are independent random variables such that probability x equal to 0 is, let's say, uh, okay, what should I choose here? Okay, let me just think for a minute, guys. Like, what kind of a distribution can we make? Or maybe like let's just not have independent random variable, but just like this kind of a giant distribution. Yeah, yeah. The probability that x is 0, y is 0 is nothing but 0.3, and then probability that x is 0 and y is 1 is 0.6. So these are the probabilities, and like note that x and y are like we are not saying that they are independent. These are the, let's say, disjoint distribution probability. And since like 0.3 plus 0.7 is 1, so this is indeed exhaustive. So suppose these are the only two possible outcomes, then we know that for this, we know that probability x equal to y is actually 0.3, because this is the only case where x equals to y. And now for finding out the total variation distance, yeah, uh, yeah, to find out the total variation distance, what do we need to find out? Yeah, so So we know that x takes the value 0 with probability 1, and y takes the value 0 with probability 0.3 and takes the value 1 with probability 0.7. So if one takes the event as like let's say just a random variable taking the value 0, then y will be taking that value 0 with probability 0.3, whereas x will be taking that value with probability 1. So 1 minus 0.3 will be 0.7. So similar to what we had in the Bernoulli example, that similar thing will be achieved here. And hence the total variation distance will actually be achieved to be 0.7 in the case. So I hope what I just said orally makes sense. That like from these distributions, like if we try to if we assume that these distributions are, if we try to find out the marginals from these distributions, then actually one can say that probability that x equal to 0 will be 1, whereas probability that y equal to 0 will actually be 0.3. And then what you can say is that if you take the event of random variable taking the value 0, then x takes the value 0 with probability 1, y takes it with probability 0.3, and then 1 minus 0.3 is 0.7. And this is the total variation distance which we obtain. So yeah. So this maximum can indeed be achieved, and so the maximum possible value of the total variation distance is just 0.7. Okay, then I guess this was it what I had for the day. Yeah, so we discussed some some questions related to like Markov chains, total variation distance, and so on. And we also discussed the brief introduction to Markov chains, which was uh, a brief summary of whatever was discussed about Markov chains in the lectures. So yeah, I guess this was it what I had from my end. Uh, so since yeah, so okay, since no one is present in the session right now, so I guess yeah. Last half an hour, I wanted to take some doubts from people, but since there are no people, like I guess there are no doubts. Uh, but maybe I'll just wait for like maybe 10 more minutes. So if someone wants to join the session to ask some doubts, then maybe they can join. If no one joins in the next 10 minutes, I'll just then close the session. So I'll mute myself till then, guys. Okay, so I guess since no one has joined the session, yeah, I guess I'll be closing the session now, and hopefully I'll see some of you guys in person next week. So yeah, thanks to everyone who's watching on YouTube. So yeah, goodbye guys. I'll be closing the session now. Thanks for watching.